Hi, my name is Cole McCullough, and today I'm going to be talking to you about an experiment that I've run of determining the amount of carbon dioxide in a soda. So carbon dioxide is a colorless gas, and it's composed of a carbon atom double bonded to two oxygen atoms. It's in the air that we breathe out, and it's in the news a lot today for its effects on global warming. So those CO2 molecules are put under pressure to dissolve into the soda, and that reacts with the water in the soda to create carbonic acid. So this carbonic acid is what provides that fizziness that many people just really love about the drink. So why does the soda go flat and lose that fizziness? Well, it has to do with Le Chatelier's principle, which states that when any system at equilibrium is subjected to a change in concentration, temperature, volume, or pressure, the system changes to a new equilibrium, and this change partly counteracts the applied change. So now let's apply this principle to our soda bottle using this chemical equation, CO2 in the gas phase to CO2 in the aqueous phase. Now, as you can see, this reaction is reversible, which means that it can go both ways. When the bottle is sealed, it's in a closed system and it's at equilibrium. However, when that cap is open, CO2 in the gas phase escapes, and since there's now less CO2 gas, the system shifts to create more using the aqueous CO2. Now, this keeps happening because the CO2 keeps getting escaped constantly, and more of that CO2 is being used until there's none left. So let's go into the actual experiment. So to capture our CO2, I used a balloon and a scale. So I first tore that scale with the balloon and an identical cap on it, and then I wrapped the balloon around the sealed 2-liter soda bottle and untwisted the cap that's inside the balloon now. So after about 8 hours, I sealed the balloon off by tying it up, and I had the cap inside, of course, and weighed it again. So as you can see, a pretty large amount of CO2 was captured, as you can see in the picture, and most of which it occurred right as the bottle was open. So the initial letting out of CO2 composed most of the volume. So once I weighed it, it was determined that I had 4 grams of CO2 in my balloon, and from there we can convert that to 0.091 moles of CO2. The majority of the remaining soda is water, so I could calculate that the moles of water using the 2-liter volume ended up being 111.1 moles of H2O. So this leaves us with a CO2 mole fraction of 8.2 times 10 to the negative fourth. So there definitely could have been some error to affect that mole fraction. First off, most likely not all the CO2 had been converted into vapor yet. If this were to sit out for a few days or even a few weeks, I believe that there would have been more CO2 that could have been recovered. Second, there might not have been a complete seal made by the balloon. There's probably better ways to seal off the CO2 rather than a 10-cent rubber balloon, which might have had leaks. And lastly, this was a very cheap scale. It kind of bounced around a good bit, and it couldn't record tenths of a gram, so meaning that our measurement was not exact. So by Googling a little bit, the most common online estimate of CO2 in a 355 milliliter Coke is 2.2 grams. So using the same calculations as before, this gives us a mole fraction of 0.025, which is about 3 times as much as my calculated mole fraction. So using that mole fraction that we calculated as well as Henry's law, we can determine pressure that the soda bottle is under before it's opened. So using this, the mole fraction of the vapor times the pressure is equal to the mole fraction of the liquid times Henry's constant, which is equal to 1,652 bar at room temperature. So plugging in our numbers, we end up with a pressure of 1.35 bar. And just if you're curious, using that same mole fraction from the online research, we would end up with a pressure of 4.13 bar, again, about 3 times as much as our calculated value. So if you ever wanted to start carbonating your own beverages, or maybe just curious about how pressurized these Coke bottles really are, now you know. And with this experiment, I hope you're able to learn a little bit about this mass transfer using Le Chatelier's principle and Henry's law. Thanks for watching.